In this video, we're going to continue on with character tables and look at character tables for molecular point groups that have irreducible representations of dimensionality higher than 1. Okay, so up here I've got some point groups, some character tables of some point groups. TD, the tetrahedral point group, has 5 different irreps. C3V has 3 irreps. C2 has 2 irreps. And what you might notice that's different about the C3V and TD than the ones we previously looked at is you have numbers other than 1 and -1. You've got 2, 3, 0, etc. So what we have here are multidimensional irreps. What we have, what we need to describe is we get the dimensionality of the irrep based off of how it behaves under the identity operator. So we have character of the identity operator in an irrep is equal to the dimensionality of said irrep. Okay, so A1 and A2 are both one-dimensional because they give a 1 under identity. E is a 2-dimensional irrep. T is a 3-dimensional irrep. We see E also in C3V. So that brings us to another term which we can define, which you might hear maybe anecdotally in the hallways, maybe in class, but still a nice term to have come across at some point, and that is an abelian point group. And an abelian point group is one in which all irreps are one-dimensional. Abelian point groups are important because in a lot of molecular simulations, you can take advantage of symmetry and speed up the calculation greatly. But generally, you can only use abelian point groups for that, or what is the highest abelian subgroup of a given point group. So oftentimes, simulations depend on what the highest abelian point group is, rather than what the total point group is if it has multiple multidimensional irreps there. Okay, so what are some examples of abelian point groups? Well, as we saw in the previous video, C1, it only has 1. C2, as I show up here, there are only 1s. CS, CI, those other very simple groups. C2H and C2V from the previous video. D2 and D2H. These are all abelian point groups. Every number in their character table is either a 1 or a -1. There are no zeros, there are no 2s, there are no 3s, etc. Okay, so the new things that we have in this video is we have E, which is a 2-dimensional irrep. And E can also have the same types of subscripts as A and B can have. It can be 1 or 2, G or U, prime, double prime, etc. All those same types of things apply to E. And similarly, we have T, which T is a 3-dimensional irrep. Okay, and then there are others as well, things that you probably won't see in most molecular point groups, but I'll bring them up just for the purposes of saying them, if it for some reason helps it stick in your brain. There's G is a 4-dimensional irrep, H is a 5-dimensional irrep, and there are other things as well. Okay, so now we've pretty much described character tables, what's in them, dimensionality of irreps, symmetry under various things, what these subscripts and labels mean, what abelian is. And I want to define, lastly, for point groups, I want to define the term order of a point group. That's going to be, I'm going to use the symbol H for that. And that's going to be equal to the number of symmetry operations of point group. Okay, and then I'm going to use the symbol d sub I as the dimensionality of irreducible representation I. Okay, so you'll notice in these in these non-abelian point groups, you have for these operators, there's the same symmetry for multiple operators that come from the same symmetry element. So there's two C3 operators that come from the C3 symmetry element. There's C3 and C3 squared. There are 3 sigma V's that they have the same character under. For the TD group, the tetrahedral group, there are 8 C3s which are symmetry equivalent. There are 3 C2s which are equivalent. There are 6 S4s, etc., 6 sigma Ds. So lots of elements are symmetry equivalent to one another. They're in what's called the same class of symmetry operations. So that that indicates that provides some additional complications in terms of our point groups. For abelian point groups, the number of symmetry elements and the number of symmetry operations and the number of irreps is all the same. So for abelian, that's 2, 2, and 2. For C2V and C2H, they're all 4. For D2H, it's 8. But for non-abelian point groups, they don't necessarily equal. So for the order, the number of operations you get from a non-abelian point group, you can calculate that by doing a sum over all of the irreps of the dimensionality squared of all the irreps. And that'll be the same as the number of total symmetry elements. So we can do an example here for the tetrahedral group and see what the order of the TD group is. So for TD, what is it equal to? So we have 1 plus 8 C3s plus 3 C2s plus 6 S4s plus 6 sigma Ds equals 6, 12, 15, 23, 24. 24 operations. But that's also the same number as if we do A1 is 1-dimensional squared plus A2 is 1 squared plus E is 2-dimensional squared plus T1 is 3-dimensional squared plus T2 is 3-dimensional squared equals 1 plus 2 plus 4 is 6 plus 9 is 15 plus 9 is 24. So we get the same answer going both ways there, no matter how we do that particular calculation. So this order and dimensionality. It's going to come up in a few equations that will be shown in later videos. So I want to introduce those and make sure you have some basic familiarity with where those terms come from, because they're going to be used in a few calculations in later videos.